Okay, good morning, guys. I hope everybody had a relaxing break there. My notebook is freezing on me, so I'm going to try to get through this in decent fashion. There's just two examples. We're going to finish this one up. Then I'm going to do the dam problem, which is number 4 on the optimization worksheet. And then from there, you can finish up whatever homework you don't have done and maybe start review so you can ask questions that you may have on our review assignment for tomorrow. So first one here is we want to find a value of a that makes f of x have a local minimum at x equals 2. Local minimum. Well, remember, minimums and maximums happen at critical values of the derivative. So I'm going to look at f of x as x squared plus a x to the negative 1, so I can take the derivative of it really nice to say f prime of x actually equals 2x minus a x to the negative 2. And as I'm cruising along here, well, now because I need critical values, I need to set my derivative equal to 0. So that's going to be 2x minus a over x squared. And if I need to know when x equals 2, to find that a, I got to plug my 2 in there. So 0 will equal 4 minus a over 4. And then from there, what I can do is I can, subtract over, or I can just multiply everything times 4, the whole equation times 4. And when I do that, I get 0 equals 16 minus a. And this thing is so glitchy, so that means a equals 16. So when a equals 16, we will have a minimum at x equals 2. And if you want to check, take f of x equals x squared plus 16 over x. Do that, graph that, and what you're going to see is we have a minimum at x equals 2. Well, the second thing we want to do here on number 7 is we want to find what value of a is going to give our function a point of inflection at x equals 1. Well, remember, points of inflection, those are like second derivative zeros, so we need to find our second derivative. So when I take this guy here, I'm going to say f double prime of x, well, that's going to equal 2 plus 2a x to the negative third, which now I got to set it equal to 0, which is going to be 2 plus 2a over x to the third. And then when I plug 1 in there, when I take my x equals 1 and I plug 1 in, well, actually what I get is I get 0. I'm glitched. I'm frozen. I get 0 equals 2 plus 2a. Well, obviously then, okay, negative 2 equals 2a. So if a equals negative 1, we have a point of inflection when f equals 1. So how would you check that? You type in your function f of x equals x squared, and it should be plus, nope, it should be minus 1 over x, and because that's a negative 1, well, it really doesn't matter. I'll leave that as a negative 1 there rather than because I'm glitchy. So remember that just is going to transfer to that's going to make that a minus there. And I just froze. So as I said before, if you plug in f of x equals x squared minus 1 over x, you will find out that at x equals 1, we will have a point of inflection at x equals 1 when that a value was negative 1. So with all the glitches going on, I'm really hoping that this isn't going to go here. So we're going to do the other part. This one was kind of a thinker problem, I think. The depth of water in Moon River, X miles downstream from Hard Rock, is d of x. Remember, d of x is going to be the depth of water. That's 20x plus 10 feet. And the width of the river is w of x, for width, obviously, 10 times x squared minus 8x plus 22 feet. To create Moon Lake, it's necessary to place a dam downstream from Hard Rock. Okay? Well, if the dam cannot be more than 310 feet wide and 130 feet above the riverbed, and the top of the dam must be 20 feet above the present river surface, where can the dam be placed? So we need to find the constraints. How far down river? We've got to find the number of miles where we can even construct this dam. Well, if my width is right here, okay, and it can't be more than 310 feet wide, I'm going to take 310, and I'm going to set that equal to 10 times x squared minus 8x plus 22. And we just need to find out, where is the river going to be 310 feet wide, basically. So I'll divide by 10. I get 31 equals x squared minus 8x plus 22. And I need to find my zero, so I'm going to subtract 31 over. And that's going to give me, what, a minus 9 here. So then I can find my zeros, and notice that's going to factor really nice for me if I quit glitching here. And I get x minus 9, and I get x plus 1. So what happens here is x equals 9 and x equals negative 1. Well, negative 1 would be up the river, so I won't even look at that. So possibly 9 miles down the river, okay? That's where it's going to get wider than 310 feet, okay? So then we also need to know it needs to be 310 feet above the riverbed. So I'm going to say, here's my depth of the river, okay? Well, if I put 130 feet here, and this is going to be 220 plus 10, okay? But if I put the 10, remember, this is giving me the depth of the river, and remember my dam has to be 20 feet above the river. So what I'm going to do here to find this constraint is I'm not going to set it equal to 130. I'm going to knock 20 feet off to find the depth of the river, so I'm going to call that 110. I'm actually looking, when is the river 110 feet deep? Because that extra 20 feet is going to be above the river. So then I get 100 equals 20x, so x equals 5. So once I'm further than 5 miles down the river, okay, I'm too deep to make the river. So my constraints are x has to be greater than or equal to 0, less than or equal to 5 miles downstream. Okay, so those are the constraints. I have to make this dam somewhere between 0 to 5 miles downstream. Okay, and we're going to go to the next one. And what are the dimensions of the widest and narrowest dam that can be constructed in accordance with the above constraints? Well, remember our constraints are right here. Whoop, not 0. They're right here to where that's 5. So I have to be between 0 and 5 miles down the river. Well, the widest. So I'm going to take my width of the river. Okay. And if I want to take W of x and I want to optimize, I want to minimize this, right? 10, that's x squared minus 8x plus 22. I'm trying to optimize. I want to find the widest and narrowest dam. Well, if I find the derivative of width, and I'm just going to take constant times 2x minus 8, I'm not even going to distribute that, and I find when is my derivative actually equal to 0? Hopefully right here we can say when 2x minus 8 equals 0, I have optimized. So I'm looking at a critical value of 4 miles down the river. Well, if I want the dimensions of the widest and narrowest dam that can be constructed, well, I also have to remember I have to be within this constraint right here. I have to be between 0 to 5 feet. So what I want to do is I want to go and I'm going to find what is the width at 0, what is the width at my critical value of 4, and what is my width of my other endpoint of 5, so I can see where is it widest and where is it narrowest. And right now I'm going to fire up my calculator and do some defining in there to find these values rather than do them longhand. Okay, so I'm back and I got my calculator here. And what I did is I'm defining W of X to equal the width of my river right there, the same way hopefully you would in your calculator. And of course, I have the stupid marker up. I got to hit enter. And I want to know what is the width of zero, or the width of the river at 0, 4, and 5 miles down. So that's why I defined it. I'm going to say what is W of 0, and I want to know what is the width at 4 miles down, and I want to know what is the width at 5 miles down so I can see where it's narrowest. So obviously it's widest right at Hard Rock, and it's narrowest 4 miles down. So what I'm going to do is I'm going to say W of 0 here was 220 feet, and here I was 60 feet, and here I was 70 feet. And if we want the widest and narrowest, we are looking at these 2 points right here, and they want the dimensions. So now what I'm going to do is I'm going to quickly grab my calculator again, and I'm going to define my my depth function in there so I can find the depth of the river and then find how high my dam's going to be. Okay, so I'm defining my depth in terms of X, and I'm going to hit enter. And so I need to know what's the depth at 0. So I want to find D of 0. So the depth is 10 feet, 0 miles down the river. And I also need to know the depth of the river 4 miles down. So remember, that's the depth of the river. We need to be 20 feet above that. So my dam needs to be 30 feet tall here and 110 feet tall 4 miles down the road. So at 0, it's going to be 220 feet wide by 30 feet tall. So those are the dimensions of the widest, and the dimensions of the narrowest will be 60 feet wide by, what were we? We were 90 feet deep, so we have to be 110 feet tall. Those are the dimensions of widest and narrowest. Narrow is down here, and widest is up there. Okay, so that gives me the widest and the narrowest river within my constraints. Okay, and the last one we're going to do here is we need to know what is the depth, or if the cost is proportional to the product of the width and height of the dam, where is the cheapest dam located? Oh boy. So cost is proportional. So I'm going to look here and I'm going to say my cost in terms of X equals, it's proportional to the product of width and length. So I need to look at this as W of X times the depth of the river. But remember, I need to add 20 feet to the height of the dam to get it above the river. So I want to minimize cost. And if the cost is proportional to width times height of the dam, remember, D of X is just depth of the river, and then I have to add 20 feet to that. So my cost function is actually going to be, the way I did it, is I'm going to look at 10 times x squared minus 8x plus 22 times this is going to be 20x plus 30, because it was 20x plus 10. And if I add the 20 to it, there's my width, and here's my height of the dam now. And this is what I want to optimize, okay? I can multiply that all out together if I wish, or I can just take it as a product, whatever you really want to do here. I'm going to take it as a product. I'm going to say the cost prime is going to be equal to, remember, this is going to be U, this is going to be my V. So my derivative of the first term is going to be 10 times 2x minus 8. And then that has to get multiplied times V. So that's times 20x plus 30. So adding the derivative of my second term, that's going to be 20 times the first term, which is 10 times x squared minus 8x plus 22. Okay, and of course now I have to find my critical values of this, which means I'm just going to do a little bit of work here, and I'm going to expand this stuff out. And when I multiply these two guys together, what I do is I get 40x squared minus 100x minus 240. And I'm just going to put these two together, and I'm going to take 200. So as I distribute my 10 to each one, I get 400x squared minus 1000x minus 2400 plus 200x squared minus 1600x plus 4400. I'm going to combine my like terms, okay, because I haven't done anything. So derivative, when I combine my like terms, is I get 600x squared minus 2600x and plus 2000. Well, now I need to find my critical values, so I'm going to set this equal to 0. And hopefully it's as obvious to you as it is to me, but there's a greatest common factor of 200 in here. I'm going to factor out a 200 of each one of these. That's going to leave me with 3x squared minus 13x plus, what, 10, right? And I'm looking for my zeros, so I'm still going to leave this. And it's non-calculator to find the values, so I'm going to say this is 3x, this is x. Obviously, I wouldn't want to put my 10 there, so then I need 13. So I'm going to say 10 here, 1 here. They're both minus, so I can see when x equals 1 and when x equals 10/3 miles down, these are my optimizing points, and I want to minimize cost, okay? So what I'm going to do, these are my critical values. So I'm going to place my critical values with my endpoints on here. And here's going to be 1, and here's going to be 10/3. Well, because 0 is not, this is not a critical value. If I put 0 in here, okay, and again, I'm rolling right into this equation right here. When I plug 0 in there, I can see this first one's a negative and a negative, which means I'm going to be increasing there. Then I'm going to take the number 2 here. I guess I probably should put my 0. So I'm increasing. So this obviously at 1, that's looking like that might be a maximum cost. And if I put a 2 in there, well, that's 6 minus 10. This one's still negative, and that's 2 minus 1. That's positive. So that's a negative times a positive. I'm going to be decreasing there. And then this is 3 1/3, so I'm just going to grab a critical value of 4. And when I put 4 in here, that's 12 minus 10 for positive. 4 minus 1 is positive, which means I'm positive right here. Well, this shows me a maximum there and a minimum here. Therefore, I have a minimum cost when x equals 10/3 miles downstream. However, I'm minimizing cost. And I also need to make sure that the cost of my endpoint of 0 or the cost of my 10/3 or the cost at 5 miles down the road, if I want to minimize cost, remember, we also have to consider our endpoints. So what I'm going to do is I'm going to hit pause, and I'm going to go type this cost function into my calculator. Okay, so I'm trying to define my cost function, and because I've already defined the width and the depth of the river, I'm going to try to define my cost. I've never done this before, as W of x times D of x plus 20. Okay, so I'm going to hit enter. Hopefully I'm defined. Now, what I want to do is I want to find what was the cost at 0 miles down the river. Now, that'd be 6,600. And I also want to know what is my cost at 10/3 down the river, or what, 3 1/3. That's going to be 6229.63. And I also want to know what is the cost at the end of the river at 5. and that would have been $9,100. So we can see we did actually minimize our cost when X is 10/3 miles down the river. So I should write all these in here quick. 0 miles, I was $6,600. And 10/3 miles, I'm $6,229.63. And 5 miles down the road, or down the river, is $9,100. That's the most expensive. And I want to make sure I answer my question. So if the cost, where is the cheapest dam located? The cheapest dam is located and right there, 10/3 miles downstream. That's where my cheapest dam is built. And that takes us there. So you got work time for the rest of the day. If you have questions, you can log into the, I'll probably have it open if you have questions on anything else. Otherwise, we'll have the chat open tomorrow the whole time. You can log in and out for questions there as well. Have a good day and make sure you reach out with any questions.